A steel giant sleeps inside a concrete canyon, hemmed by walls that rise like cliffs and cranes that hang like patient birds. A single command sets valves turning, and a managed flood begins to whisper, then roar. Hundreds of millions of gallons surge inward, not as chaos, but as choreography. Inch by inch, the colossus lightens, testing the water's grip. Hours later, it loosens from its cradle and tastes buoyancy for the very first time. It feels like witnessing geology move. Keep watching, because there is a counterintuitive moment in this ritual. Subtle, brief, and more perilous than the dramatic first float. We will reveal it later in this video. Before we begin, make sure to hit the like button. It helps us beat the YouTube algorithm. The stage for such transformations is a graving dock, a monumental basin that can be rendered bone dry for years, and then, on a chosen day, turned into a harbor. Along a tidal river in Virginia, these docks stretch a distance measured in city blocks, wide enough for teams, cranes, and modules the size of townhouses. Their floors are laid with survey marks as tidy as graph paper. Above them, gantry cranes glide on rails, lifting prefabricated sections that arrive like puzzle pieces, hull blocks, island sections, catwalks, and decks already threaded with pipes and cable runs. Construction begins with the keel blocks, a grid of reinforced concrete shapes capped with wood and set on coordinates derived from laser surveys. Each block carries a planned portion of the load, so the hull's weight spreads like a hand across many fingers. Ship fitters align the first plates to reference lines, tack weld them, then close seams with beads that look like ripples frozen in time. As the hull rises, compartments take form: machinery rooms, aviation fuel cells, chilled water loops, and galleries of switchgear that will later hum with electrical life. Before we continue, make sure to hit the subscribe button. It really helps the channel grow. While the structure grows, specialists carve pathways for power and data. Cableways run like arteries within bulkheads. Brackets fix every bend to prevent chafing. Labels and barcodes track the destiny of each line. Pipe fitters install fresh water, fire main, and low-pressure air systems, hydro-testing each run to verify integrity. Ventilation trunks weave overhead, sized to whisk away heat from electronics and to feed clean air to workshops below. The empty spaces begin to feel like a city under scaffolding, with streets, alleys, and addresses that cross on frames and decks. Before water is ever invited in, inspectors perform a ballet of measurements. Coating technicians verify paint thickness on the underwater hull to resist fouling and corrosion. Shaft lines are aligned against micrometer readings. Rudder stalks are checked for smooth travel and perfect seals. Temporary services, electricity from shore, breathing air for welders, fire hoses at the ready, remain in place until the final safe-to-flood checklist is signed. When the day arrives, watchstanders take their posts along the dock walls, clipboards in hand, radios clipped to vests. Flooding does not begin with a dramatic deluge. Operators open culverts in carefully timed stages, bringing the water to the first target level, just high enough to touch the lowest blocks. Gauges track the rise. Lasers watch for any hint of twist. Even in these early inches, the ship's massive weight begins to share itself with the water. Sound teams listen for creaks that are normal and those that are not, while engineers watch tiny witness marks painted on structural members for unexpected movement. Everything slows to the tempo of precision. At the next plateau, the sea takes more of the burden. The hull, until now a monument pressed upon stone, begins to consult the water for support. Ballast engineers adjust internal tanks to keep trim and list within strict tolerances. A fraction of a degree matters when a vessel spans longer than a trio of football fields. The goal is even ascent. No sudden pivot. No bow-heavy slump. No stern trying to rise before its partner. The carriers of the future are born with patience, not spectacle, and patience here means safety. As the level climbs to the final marks, the keel clears the blocks with calculated margin. Dock crews ease working lines across mooring bits set into the walls. Tugboats idle like draft horses waiting for reins, their pilots watching flags for the faintest breeze. Even a light wind pressing on the island can matter. The ship's profile is enormous, and water at rest is never perfectly still. Commands pass calmly. Heave, slack, hold. The city of steel inches toward the open gate, guided as much by math as by muscle. Ceremony often arrives on the same day, but ritual and readiness are different clocks. The christening belongs to tradition. The system's checks belong to reality. Crews circulate through machinery spaces, confirming that valves, pumps, and breakers respond on demand. Fire main is charged and bled. Communication circuits carry clear voice end to end. Watertight doors close with the correct bite on their gaskets. Only when those practical proofs are satisfied does the ship leave the dock and sample the current of the river with its own weight, its own momentum. Once in the river, The vessel transitions from object to instrument. Dock trials verify anchors pay out and recover smoothly, that capstans pull without stutter, that bow and stern respond predictably to thruster nudges. The helmsman feels how the ship pivots, judges the distance needed to stop, and records how the hull answers rudder angles at low speed. On the bridge, navigation teams compare electronic charts with visual ranges along the riverbanks, building a mental map that will carry them safely to deeper water. At sea, propulsion teams bring shafts up in steps, listening through accelerometers for any hint of misalignment. Engineers cycle electrical loads, shifting between generators to prove redundancy across the distribution buses. In aviation spaces below, teams test aircraft elevators, doors shut, interlocks verify, platforms rise and fall with a steadiness that reassures. On the flight deck, jet blast deflectors hinge up and down as if breathing, rehearsing for the tempo of launches that will later define the ship's daily cadence. Where previous generations relied on steam catapults, the newest decks employ electromagnetic launchers. Instead of boiling water into driving vapor, linear motors summon a moving magnetic field that hauls a shuttle down the track. The shape of that push is adjustable. Lighter aircraft can be treated gently, heavier aircraft firmly, all while staying within envelope limits that preserve airframes. Reset cycles shorten, maintenance footprints change, and the deck gains the ability to serve both crewed fighters and unmanned aircraft with equal confidence. Landings evolve as well. Arresting gear once dominated by hydraulics now marries mechanical strength with digital control. Energy absorbers can be tuned to meet each approach with the right resistance, smoothing out variations in aircraft mass and speed. Early deployments surfaced reliability challenges. No surprise for systems at the frontier. Engineers responded the way good engineers do: isolate faults, redesign components, refine software, and test across thousands upon thousands of cycles until performance becomes boringly consistent, which is exactly what safety demands. Behind the machinery stands a workforce whose craft borders on art. Welders qualify through grueling tests, then spend years stacking steady beads in awkward corners where mirrors and headlamps guide their eyes. Pipe fitters route lines through labyrinths of frames, avoiding traps where air might hide or sediment might settle. Electricians check insulation resistance, continuity, and bonding points to ensure that power flows where it should and never where it should not. Every action is recorded so future maintainers can trace any mystery back to its birth. Supply chains link far-flung towns and cities. Plates roll from mills, complex castings travel from foundries, precision bearings arrive wrapped like jewels. Software updates flow from teams who live in version control. The shipyard itself trains new apprentices under the mentorship of veterans who have seen whole classes of vessels rise and deploy. Knowledge is communal and cumulative, passed across lunch tables and toolbox talks, captured in procedures and also in the quiet intuition that tells a craftsperson when something feels not quite right. Schedules stretch or compress for reasons both predictable and human. A redesigned component might promise fewer failures over decades, but it also might require reworking nearby systems now. A supplier could face workforce shortages or a materials delay that ripples outward. Rather than rush to meet a calendar, program leaders weigh risk against readiness and often choose the slower path that builds reliability. The result is a ship better prepared to serve safely across long deployments and harsh environments. Operationally, a carrier is not a soloist. It works within a strike group whose escorts provide layered defense and whose logistics ships sustain the tempo. Shared data stitches hulls together into a moving network. Radars pass tracks, sonar arrays compare signatures, and aircraft deliver reconnaissance that becomes a common picture. The group can deliver aircraft inland, coordinate humanitarian relief after storms, or maintain presence that reassures partners. The same deck that launches jets can lift helicopters loaded with water makers, medical gear, and shelter supplies. Economics thread through the story. Building and sustaining a carrier supports a constellation of skilled jobs and technical apprenticeships. Investment in power electronics for electromagnetic launch, for instance, spills into civilian sectors that benefit from robust high-efficiency converters. Predictable construction plans enable suppliers to invest in better tooling and quality systems, which in turn lowers defects and raises confidence for future projects. The industrial base grows steadier, and steadiness is its own kind of strength. Internationally, allied navies watch, learn, and sometimes adopt. Electromagnetic launch and the latest arresting gear present attractive options for partners planning new decks, especially those anticipating mixed air wings with both crewed and uncrewed aircraft. Knowledge exchange runs in both directions. Deck handling practices, safety signage standards, and maintenance philosophies travel across oceans, refining everyone's methods. Interoperability grows not only from shared radios, but from shared habits that make joint operations smoother and safer. These carriers are designed with growth in mind. Space, weight, cooling, and above all electrical power are reserved for tomorrow's systems. Today, only a portion of generating capacity is consumed. The rest stands ready for directed energy defenses, more sensitive radar arrays, enhanced electronic warfare suites, or technologies we have not yet named. This margin is not extravagance. It is foresight, the architectural equivalent of leaving sturdy beams in place so higher floors can be added without rebuilding the foundation. Life aboard settles into rhythms that emphasize reliability. On the flight deck, colored jerseys move with practiced choreography. Directors, fuel teams, ordnance crews, and crash and salvage specialists in their distinctive gear. Below decks, planners track sortie generation, turnaround times, and maintenance intervals, looking for small improvements that compound over weeks. In engineering, watch teams monitor temperatures, vibrations, and power quality on screens that glow in the dim light of machinery spaces. Alert to trends that whisper before alarms shout. Safety culture wraps the entire enterprise. Near-miss reports are treated as gifts rather than confessions. They help the team widen margins before luck is needed. Drills rehearse fire, flooding, and medical response until muscle memory takes over. Deck markings are bright and unambiguous. Hand signals are standardized and reinforced in training videos and on-the-job shadowing. The goal is not to eliminate risk, that is impossible at sea, but to manage it so thoroughly that even surprises find crews ready. When the ship returns to port, the learning continues. Inspectors open manways, sample oils and coolants, and compare recorded data with crew narratives. Planned modernization brings in the next round of upgrades. Smarter power converters, hardened networks, refreshed sensors. The feedback loop turns each deployment into an investment that improves the fleet. In that way, the class evolves quietly, ship by ship, toward greater effectiveness with fewer surprises, an upward slope built from thousands of tiny, careful corrections. Now the promised reveal. The most delicate instant is not the famous first float when the hull is fully free. It arrives just before, in the narrow window where buoyant force almost equals weight but not quite. In that liminal moment, a small asymmetry can load the structure in unexpected ways. To protect against that, engineers plot a flood curve with pauses at precise levels, trim ballast to balance the hull, and verify clearances at critical blocks. Pass through that window smoothly, and the rest of the ascent becomes routine. Sea trials expand the envelope in carefully staged steps. High-speed runs test propulsion and steering under load. Crashback maneuvers verify stopping power without overstressing shafts. Tight turns measure handling and reveal any hidden vibrations. On the deck, launch and recovery cycles scale from a few evolutions to sustained operations over many hours. Data analysts compare real performance to digital models, then adjust maintenance intervals to match reality rather than hope. Only after this evidence stacks up does formal acceptance proceed. The air wing itself is a composition rather than a single instrument. Strike fighters bring reach. Airborne early warning platforms expand the horizon. Helicopters carry sensors, supplies, and rescue capability. Unmanned aircraft extend endurance and reduce risk in dangerous neighborhoods. The electromagnetic launchers and modern arresting systems give the deck the flexibility to serve this orchestra, changing tempo and mix without mechanical complaint. That adaptability is a quiet multiplier, no headline captures, but every planner prizes. Human stories thread through the steel. Families in shipyard towns pass down skills like heirlooms, a way to read a weld's color, a knack for coaxing a stubborn flange into perfect alignment, a method for lacing cables so they never sag. Sailors rotate aboard as learners, then return as leaders, carrying lessons that become doctrine. Pride here is practical. It shows up in checklists kept crisp, in decks painted on time, in tools returned to their racks, and in the knowledge that small disciplines add up to large reliability. Over decades, refueling and complex overhauls will pause each nuclear-powered hull for deep renewal. Those yard periods are opportunities as much as obligations to insert new radar faces, refresh computing cores, reroute cable trunks for future growth, and replace wear-heavy equipment with sturdier designs learned from years at sea. The ship that returns to the fleet after such a period is not the same as the one that arrived. It is a veteran with new strength, carrying the past forward in a better form. Globally, the presence of a carrier strike group reshapes calculations without firing a shot. Partners feel supported. Potential adversaries reconsider. Yet the same platform that can project combat power can also deliver relief after earthquakes and storms, generating fresh water, medical care, and transport at a scale that arrives quickly to coastal regions. That dual capacity, deterrence, and assistance, explains why nations invest in carriers even when they are costly. Flexibility earns its keep across the unpredictable narrative of the world. Costs, often discussed in headlines, are best understood across lifetimes. A carrier serves for half a century or more, its value measured not only in hardware, but in the readiness it enables and the crises it steadies. The choice to incorporate growth margins, to accept deliberate tests, and to update systems methodically may look slow in a single year, but wise in a single decade. In that long view, reliability is inexpensive, and surprises are the most expensive line item of all. The engineering behind electromagnetic launch offers a concrete example of that philosophy. Power is drawn from robust generators and shaped by converters into the pulses that feed linear motors. Those pulses are timed and scaled to the aircraft's mass and desired end speed, translating equations into motion with fidelity. Each evolution is logged, allowing maintainers to spot patterns: a bearing warming sooner than expected, a sensor drifting, a module cycling harder than its peers. Data becomes prevention, and prevention becomes tempo. Below decks, the human infrastructure mirrors the physical. Training pipelines keep new technicians flowing in, simulations rehearse rare but critical scenarios, and cross-rating collaboration spreads insight beyond silos. The culture encourages questions and rewards the candid phrase, "I do not know yet." That posture makes room for discovery and makes it safe to surface small issues early when they are easy to fix. An organization that learns in small increments avoids learning suddenly in crisis. Even the paint tells a story. Specialized coatings below the waterline discourage marine growth and shave drag, saving fuel over years. Non-skid textures on the flight deck protect boots and wheels, renewed in scheduled sections so operations never halt. Color codes on pipes, freshwater, fuel, fire main, hydraulics, turn complexity into legibility, so a new sailor can identify a system at a glance in smoke or steam. These small, standardized choices compound into safety and speed when seconds matter. Remember to hit like and subscribe. Thank you so much for watching. Your support means a lot.